All right, good morning, everybody. It's about 11 o'clock, so I guess we'll get started. Today we're going to be starting a totally new topic, clean after break. Hope you all had a good Thanksgiving break, by the way. Um, we're going to be talking about global warming and climate change, which is kind of outside of the wheelhouse of what we're normally talking about in this course. But for a couple different reasons, we're going to spend a week talking about this. Number one is it's such an important subject that's, really one of the most important things to be literate about in the scientific kind of world today. And number two, those of you who are following along in the textbook for the course, um, our textbook author is actually a pretty famous name in the world of global warming and climate change. So I'll talk about that a little bit later on. But that's why there's a chapter in the book about it. It's something that he's really interested in. So I am kind of following suit. Although if you're following along in the textbook, I'm doing a very different presentation from what he does in the book, partially because the textbook is getting kind of old and out of date, and also because the textbook goes on a few kind of tangents. I really wanted to focus more on the main story. And that main story is, for today's class, I really want to address the first two questions on the list here. What is global warming? Is it real? How confident are we about that? And what is the cause of it? What is the scientific explanation for it? And how sure are we that that is the scientific explanation for it? This is kind of like the basic foundational knowledge that you need in order to speak the language of, even having an opinion about global warming and climate change. So as always, feel free to ask questions if you have anything as we go here. I'm sure people will have some questions, but I'll try to keep my presentation as to the point as I can. And also, by the way, I'm trying to keep it as apolitical as I can, and just focus on kind of giving you the real scientific basis that you need to form your opinions about it. The other thing I want to do before we get started in this chapter is talk a little bit about sources, because there's so much wrong information out there, frankly, about global warming and climate change. It's actually a difficult subject to research on your own. It's not something that you can just Google and find accurate information. You kind of already have to know the basics in order to figure out what you're looking for. So I wanted to mention where I got most of my information in this chapter, because these might be useful references for you later if you want to update yourself about what's changed since you took this course, which, things change practically every year in terms of learning new things and updating on the situation of what's happening. So the first and most important source to be aware of is what's called the Intergovernmental Panel on Climate Change, more commonly known as the IPCC. And this is an international organization which is affiliated with the UN. And its job is, people use this word of a scientific consensus on global warming. The job of this organization is basically to assemble all these little bits and pieces of science that are done around the world and put that together into a consensus that just about every scientist in the world who's working on this would agree with. So number one, that makes them a really great source, because their job is literally putting together the scientific consensus on this. And number two, they do a really nice job of updating this information every few years. They're very reliable, and it's kind of like the gold standard in this community. So if you want to know 5 years from now whether anything's changed since you heard this PowerPoint presentation, what you would want to do is look up the latest IPCC report. And it's also great because the IPCC, although it's made up of scientists, it's designed, its purpose is to communicate with non-scientists. So the reports actually are very readable. They're meant to be read by politicians and the public and people who don't have that much background in the field. So that also makes it a great source because it's both accurate and understandable. So since sources are so important in this chapter, every time I quote the IPCC, I'm going to use this yellow highlighted font that you see on the screen right now, and that font will remind you that that quote is coming from the IPCC. The main source from the IPCC that I'm using is the 2014 synthesis report, which is their most recent, like, big major report that they released. And you can find it here if you want to read the whole thing. And please feel very, very encouraged to just read the whole thing. Like I said, it's very readable. You can read it in an afternoon, and it really contains a lot of really good information, which I'll be summarizing in this presentation. They also released another report, kind of a mini update in 2018, which people refer to as the 1.5 degrees Celsius report. And I'll also use a slightly different yellow highlighted font when I am citing that source. So again, yellow highlighting means IPCC, and the two different fonts mean telling you which report you can go to if you want to see the context for that quote. And then the other major source that I'm using is what's called the Berkeley Earth Project. And this is actually the organization that was started by the author of our textbook, is one reason why I'm using it. And the other reason is because it's also a very accurate and concise and understandable kind of conglomeration of all the information that we have about global warming and climate change. So whenever I'm citing either the Berkeley Earth Project directly or our textbook author in some other context, I'll use this red highlighted font. So you know that's coming from our textbook author, Richard Muller. Okay, so let's get started. I decided the way to structure this presentation was really not to try to be dramatic and keep you in suspense or anything like that, but just to get right to the point and try to make it as clear as possible. So the first section is things that there really can be no debate about whatsoever. Things that are just simply measurements, observations, which have been made and which really created this whole discussion about the fact that global warming was occurring. And what we know from these observations is that global warming is occurring. And again, that's not a statement of really interpretation. It's not a statement with any political content. It's literally an observation that the temperature of the Earth is going up for some reason. We'll talk about the reason later. And so we know that because literally we can measure the temperature on Earth and we see that it's going up. And then also we know that the amount of snow and ice on the Earth are decreasing, and also that the sea level is going up. So let me show you that information before we try to do any kind of interpretation where things might get in any way more controversial. Okay, so first of all, again, first statement right off the top is that global warming is definitely a real thing that is happening. There's no debate about that. In the words of the IPCC, they say that warming of the climate system is unequivocal. And the word unequivocal for the IPCC is like such strong language, because they're kind of in some ways a very timid organization where they don't want to be caught saying something which is not accurate for obvious reasons. So they're very careful with their language. They actually define words like unequivocal in the appendix of their report. And unequivocal, on their scale of different words that they use, it's the highest word on the scale. And, you know, basically means we are 100% certain about this, that the climate is warming. And what does that mean? It means the atmosphere and the ocean have warmed, the amount of snow and ice have diminished, and sea levels have risen. And the Berkeley Earth Project makes very similar statements. In their words, global land temperature has increased by about 1.5 degrees Celsius over the past 250 years. Let me show you the data on this. So this graph is coming from the Berkeley Earth Project website. They have some of the nicest graphs, and they're also updated frequently. So this shows you the average temperature of the Earth from 1850 up to today. And the y-axis, you can see it's labeled as temperature anomaly. This is the way they report this. It's basically just the temperature of the Earth compared to some reference temperature, which is called zero. So basically you can see now that the temperature currently is maybe 0.9 degrees Celsius above that standard level. And in 1850, it was maybe 0.5 degrees Celsius below that standard level. So that's an increase of like between 1 degree Celsius and 1.5 degrees Celsius since 1850. Now, the exact number there is going to vary a little bit depending upon exactly the temperature of what. Some people will use the temperature of the water, the temperature of the land, the temperature of the air, et cetera, et cetera. So there can be a little bit of differences because of that. But no matter which measure you use, the temperature of the Earth is clearly going up over this time period. You can also see how there are fluctuations from year to year. The graph does not go up every single year. It does, shake up and down because of differences, in the weather from year to year and things like that. But you can see that clearly there's a general upward trend, especially since the mid 20th century. This last part of the graph here is where the effect is really, really exaggerated. Okay. If you go back even further, it starts to get more and more difficult to accurately measure the temperature the further you go back. But one of the contributions of the Berkeley Earth Project was accurately going back to 1750, whereas most people just go back to 1850. And what you can see there, in this case, the black line is the best guess of what the temperature was at that time, and the gray shading represents uncertainty. For various reasons, because of the measurements that were used, because there's not that much data available, et cetera, et cetera. There's more uncertainty in what the real temperature was, but you can see that clearly it was not warmer in 1750 than it was today. And it appears to be about not very much change from 1750 to 1850. So the statement remains the same, that there's an increase of about maybe 1.5 degrees Celsius from 1850, and also an increase of maybe 1 to 1.5 degrees Celsius from 1750. And you can also see on this graph, this graph is coming from the Berkeley Earth Project, and they actually compare several different measurements here, several different groups that are trying to measure the temperature of the Earth in different ways. And the details aren't that important, but what you can see is if you look at how those graphs compare, everyone is essentially in agreement to within very small differences in what the temperature is. So it's not like there's organizations out there that are reporting totally different temperatures from everyone else. Any disagreement in what the temperature is like a tiny fraction of a degree difference. So everyone's reporting the same temperatures basically. And everyone is saying that the temperature is going up, no matter how you look at it, no matter how you measure it. Okay, I already talked about that. One measure that's maybe a little bit less obvious, but even more clear, is if you look at sea level rise. This graph, this is from the IPCC report, and this shows sea level rise from 1900 up to when this report was published, which was 2014. And you can see how, once again, there's a bunch of different lines based on using different sources, and everyone's in agreement that the sea level is gradually going up. One thing that's nice about the sea level measurements is that there's less of that kind of random fluctuation from year to year. So it's even clearer that things are going up from one year to the next. And if you look at the scale on the y-axis there, that's in meters. And again, it's compared to some standard reference temperature that we're calling 0. So if you look at how much it's changed on that scale, it's about 20 centimeters of sea level rise over the 20th century, basically, which corresponds to about 8 inches in American units. So it's a pretty significant amount. And by the way, you might pause for a second in the back of your mind here and say, what does sea level rise have to do with warming? So why would warming cause sea level rise? The most obvious reason is because melting of glaciers and different snow and ice sends more water into the ocean. And then there's also a secondary reason. Anybody remember what the other reason is? We talked about this in a previous chapter. why warming causes the sea level to go up? Anyone remember that? We talked about this way back when in chapter 2. No? I'm talking about the thermal expansion effect. That when you warm up the ocean water, it actually gets larger simply because it gets warmer, because the molecules take up more space as they vibrate more due to the higher temperature. So for several reasons, the ocean expands and also gets more volume as the temperature goes up. Okay, so that's basically the data. That's what we need to explain. The temperature is going up, the sea level's going up. This has been observed over a period of time by many different sources. So then the next question is why? And this is where you have to add in a little bit more interpretation and kind of a little bit more theory. But again, I'm not going to try to keep you in suspense. The answer to this question is, well, first of all, the greenhouse effect. You probably already know about this. I'll explain that a little bit more. So the scientific consensus is that the greenhouse effect is what's causing the warming, that it is caused primarily by human beings. And how certain are we about this? The IPCC report says that we are about at least 95% certain that that is the correct explanation. So when people talk about whether there's like a debate about global warming, I mean, the cause of global warming, it's not, you can't say that it's 100% agreement by everybody, because there are other ideas out there, but everyone is pretty much convinced that all the evidence seems to be pointing in the same direction. And that direction is greenhouse effect caused by fossil fuels and other man-made sources. And one of the big, I'm going to go through very carefully now a lot of the evidence of why we think this is the case for the whole next section. But one overall thing that I want you to keep in mind while I'm giving you all this different information is that the conclusion that the warming is caused by human beings via the greenhouse effect is not something that's based on one single theory or one single piece of evidence. It's coming from a lot of different pieces of evidence, which are all pointing us into the same direction. So this is one reason why we can be so confident that this explanation is correct, because there's no one thing which, you know, even let's say that we found out tomorrow that one of the key things that I'm about to present to you is actually totally wrong and the experiment was like had some major flaw or was faked or whatever. It actually wouldn't affect the overall conclusion that I'm about to tell you, because there's so many different pieces of evidence which are all pointing towards the same direction. So the conclusion is not based on any one piece of evidence, which is what makes it so robust. So let me tell you a little bit more about that. First, well, since I'm a physicist, I want to start with the really basic physics before I start getting into the details. And this is going to call back to a lot of other things that we've talked about earlier in the course. A basic fundamental question to start with is, what determines the Earth's temperature in the first place? Why is the Earth the temperature that it is? And what we learned way back in the beginning of the course is that, first of all, temperature is energy. Temperature is basically a measure of how much energy is in the Earth. And the amount of energy in the Earth, we have this conservation of energy principle going all the way back to day 1 of the course. We have this conservation of energy principle that energy cannot just appear. It has to come from somewhere, and it cannot just disappear. It has to go somewhere. So where does the energy come from on the Earth? And the answer is, well, it comes from the sun. So the Earth absorbs energy from the sun. And where does that energy go? Why doesn't it just pile up forever and the Earth keeps getting hotter and hotter and hotter? And that's because the Earth gives off energy into outer space. through the mechanism we just talked about before break in chapter 9. We talked about how every object in the universe, whether it's living or inanimate, whether it's a planet or a book or a person, everything in the universe is constantly giving off energy in the form of light. Our bodies mostly give off infrared, and so does the Earth, actually, because the Earth is, in the grand scheme of things, approximately the same temperature that we are. So it mostly gives off its energy in the form of infrared light that escapes into outer space. So the overall idea here is that in general, you would expect that those two effects would be balanced with each other, that the amount of energy that's coming into the Earth from the sun, mainly in the form of visible light, is approximately balanced with the amount of energy that's leaving the Earth, mainly in the form of infrared light. And if those two are balanced with each other, the temperature of the Earth remains about the same over time. So if the temperature of the Earth is changing, what you would expect is that somehow the balance between those two things has been thrown off. So how could that balance get thrown off? Well, we have this idea called the greenhouse effect. And this is based on something that we haven't exactly said anywhere in the course, but we've hinted at a few times, which is that when it comes to light, there are many substances which are transparent to one form of light, but not transparent to another form of light. A very simple example is sunscreen. We talked about in chapter 9, how sunscreen is transparent to visible light, which is why you can't see it when someone is wearing sunscreen, but it's opaque when it comes to ultraviolet light, which is why it can block the ultraviolet coming from the sun and block you from getting a sunburn and so on. We also talked about, like, with X-rays. X-rays can penetrate the skin, but they can't penetrate the bones in your body. So that's another form of light that can penetrate one substance, but not another substance. Well, it turns out that there are gases in the Earth's atmosphere which are transparent to visible light, but they are not transparent to infrared light. And because the energy that's coming into the Earth is in the form of visible light, but the energy that's leaving the Earth is in the form of infrared light, they allow the light to get in, but they don't allow the light to get out afterwards. So that's the essential idea, that the amount of energy that comes into the Earth is basically constant over time, because it only depends how much energy is coming from the sun. But the amount of energy that's going out from the Earth depends how many of these greenhouse gases you have in the Earth's atmosphere. So these greenhouse gases hold the heat in and basically keep the Earth warm. Now, that's not necessarily a bad thing. We need greenhouse gases in the atmosphere, because without greenhouse gases, the Earth would be extremely cold. Not very different really from, like, the moon or Mars or something like that. But then on the other hand, if you have a lot of greenhouse gases, you have a situation similar to what we see on Venus, for example. Venus is famously incredibly hot. What a lot of people don't realize is the reason why Venus is incredibly hot is actually not because it's that close to the sun. It's really not that much closer to the sun than the Earth is. The reason why Venus is so hot is because its atmosphere is made largely of greenhouse gases, whereas the Earth's atmosphere only contains a small percentage of greenhouse gases. So the composition, the amount of greenhouse gases in the atmosphere determines whether you have a planet which is ice cold all the way up to, boiling hot, and it could be anywhere in between. And I got a question privately in the chat about the infrared light, like, where is this infrared light coming from that's trying to escape into outer space? That is going to call back to chapter 9. In the section on infrared light, we talked about this actually, that the molecules of a substance are constantly in motion because of its temperature, because of the thermal energy. Remember, temperature basically means that the molecules of the material are in motion. And whenever you have a charged particle in motion, like the protons and electrons in your body, it causes it to emit light. So that's where the infrared is coming from. It's actually coming from the motion of the atoms inside every object that makes up the Earth. All the atoms that make up the Earth are vibrating, and those vibrations are producing infrared light in the same exact spirit as chapter 9. Okay, so into a little bit more detail. The most famous greenhouse gas, not the only one, but the one that people are pretty much fixated on talking about in the political realm, so I'll fixate on it as well, is carbon dioxide. Carbon dioxide is a greenhouse gas, which it actually makes up only a tiny, tiny percentage of the Earth's atmosphere, about 0.1%. But it's a pretty potent greenhouse gas. So even a concentration of 0.1% in the atmosphere makes a pretty significant difference in determining the Earth's temperature. As you all know from, sixth grade science class or whatever, carbon dioxide comes from all the animal life on Earth. When we breathe, we absorb oxygen from the air and turn it into carbon dioxide. And then on the other hand, plants, when plants breathe, they absorb carbon dioxide from the air and turn it into oxygen. So naturally speaking, animals are giving off carbon dioxide, but plants are absorbing it. So overall, these are usually approximately in balance with each other, and the amount of carbon dioxide in the atmosphere remains about the same over time. Where things started to change was that there's another source of carbon dioxide that's important, and that is when you burn fossil fuels. Because fossil fuels, what they all have in common is that they contain carbon, and when you burn them, that carbon combines with oxygen in the air and turns into carbon dioxide. So when you burn fossil fuels, it creates more carbon dioxide in addition to the normal levels that are being produced by animals. And there is no kind of natural offset to that. So the more fossil fuels you burn, the more carbon dioxide gets emitted. And that carbon dioxide just keeps on piling up and piling up and piling up in the atmosphere with nowhere for it to go. And it causes the carbon dioxide levels in the air to just keep on building up and building up and building up. And that's basically the story of the greenhouse effect and what it has to do with human activity, what it has to do with fossil fuels, and all these other things that you've heard about. So that's like the key synopsis of sort of the theory, the story that goes behind everything. So next up, I'm going to shift gears and talk a little bit about, right now, this is just a theory. If you're approaching this with a skeptical mindset, you might have a lot of questions still and a lot of doubts still, because I haven't proven any of this yet. I've really just given you a story. So the next step is to go through a little bit more carefully of why do we actually think that this story is what's really happening? What evidence do we have that this story is the actual, most important explanation for what's going on? So that's next on the agenda. And I'm going to kind of build up this story by voicing some of the common objections that people have to when people talk about this story, and I'll kind of answer those objections as we go. Because actually, by the way, one of the little subtle themes, and I'll talk about this at the end of today's presentation, is that when you have these objections, that's fine. These are legitimate questions, but they're also questions that can be answered. So, it's fine to raise skeptical questions, but then you have to be willing to listen to the answer after the question has been raised. So the first objection I'm going to raise here is, I often hear people say that, like, well, sure, fossil fuels emit carbon dioxide, but I have a really hard time believing that human beings could possibly be emitting enough carbon dioxide to throw off the balance of the atmosphere. That sounds crazy. There's no way the amount of carbon dioxide we're producing could be that much. So let me address that. There's actually a couple things to mention in addressing that. First of all, I want to remind you of something I already said, which is that the amount of carbon dioxide in the atmosphere is only about 0.1% of the atmosphere. So it actually does not take much at all to throw that percentage off, because it's not like you have to change the atmosphere composition like by 10% for this to be a significant effect. You only have to change it by like 0.01%. And it's already a significant change because it's such a small amount that it only takes a small amount to, let's say, double it. Would only take a change of 0.1%. So it doesn't take as much as you might think based on how big the Earth is. And then the second point that I wanted to make is that this question, like many of the questions that people raise about global warming, this question is not one that we have to philosophize or speculate about. This is an answerable question because you're basically asking, if you take that question and just rephrase it as like a scientific answerable question, you're asking, how much carbon dioxide do we actually put into the atmosphere? Well, that's a question we can answer, and I'll show you the answer. Okay. The current answer is that we're putting about 42 billion tons of carbon dioxide into the air per year. As of 2018, I think that number is from. And here's a graph from the IPCC report where you can kind of see this in action. You can see on this graph here, the y-axis is billions of tons of carbon dioxide released per year. And the x-axis is the year. The gray is the amount that's coming from fossil fuels and some other industrial processes. And the brown is coming from basically deforestation and things like that. So the other term to be aware of is in the title here, you can see this is labeled as global anthropogenic carbon dioxide emissions. Anthropogenic is an important word to learn if you want to speak the language of global warming. It's the biggest piece of jargon, or one of the biggest pieces of jargon that everyone uses. Anthropogenic simply means man-made, caused by human beings, not caused by a natural effect, caused specifically by human beings, human activity. So this is just the amount of carbon dioxide that's coming from human activity, human industry, especially burning of fossil fuels. So what you can see here is that back in like 1850, the effect of human beings was not really that significant. It was only a couple billion tons of carbon dioxide per year, mainly because of deforestation. But then in the 20th century, and especially the late 20th century, you can see about 1950 is when this effect really starts to go crazy. It just skyrockets. And we go from producing just a few tons of carbon dioxide per year to 10 times that amount in a matter of just, one lifetime. And that is what people are talking about with really why this is kind of like a crisis situation, because the rate has just gone up a ridiculous amount in the past, let's say 75 years. A couple, I already mentioned that, a couple quotes from the IPCC report that really jumped out at me on this topic. One was that emission of carbon dioxide from fossil fuel combustion and other industrial processes contributed about 78% of the total greenhouse gas emission increase from 1970 to 2010. So in other words, the vast majority of carbon dioxide increase has come from fossil fuel use and these other related processes. So definitely, number one, it is fossil fuel use that explains where all these greenhouse gas emissions are coming from. And then number two, another quote that really jumped out at me was about half of anthropogenic carbon dioxide emissions between 1750 and 2011 occurred in the last 40 years of that time period. So, you know, it's like in 1 decade, we're now producing more carbon dioxide than we produced in, you know, centuries of man-made activity earlier in history. So the amount even that we produce in 1 year now is, you know, as much as we would produce in a decade or more in the 1800s, let's say. So we're producing a lot more greenhouse gas emissions than we were just a few years ago. The other thing I wanted to highlight, I added this red circle to the graph here. I just want you to keep in mind as we go over to the next couple slides, this feature on this graph, where right around 1950 is when the graph takes a dramatic upward turn and starts kind of accelerating out of control, because that'll come up again shortly. Okay. All right. Now, as we go through this story, because I know I'm throwing a lot of information at you, I'm gonna keep building up kind of this summary of the story and reminding you of what we've done so far. So right now, the summary is quite short, but it will keep getting longer as the presentation goes on. So for now, I've given you one piece of evidence, which is that we're releasing a lot of carbon dioxide into the air, mostly since the 1950s and mostly because of fossil fuel use. Okay. So of course, that doesn't really prove anything yet. You may still have many skeptical questions in your mind. Another one you might have is, well, okay, fine, we're emitting a lot of carbon dioxide into the air, but that doesn't necessarily mean that the carbon dioxide we're emitting is throwing off the composition of the atmosphere. Maybe, like I told you a few minutes ago, that the carbon dioxide we put into the air stays there, but who's to say that's true? Maybe the carbon dioxide that we put into the air gets removed through some natural process that we don't understand. Just because we're emitting carbon dioxide doesn't necessarily mean that it's staying in the atmosphere and throwing off the composition of the atmosphere. But once again, the answer to this question is, well, you're asking a question that has a very clear answer there. You're asking the question of, is the composition of carbon dioxide in the atmosphere actually going up? Well, let's check. Here is the composition of the atmosphere of the three main greenhouse gases. Carbon dioxide is the one that we're going to focus on. The other two key ones are methane and nitrous oxide. Just suffice it to say that they all have the same upward trend. And that's all I'll say about methane and nitrous oxide. But anyways, the green is the carbon dioxide. And you can see how it's definitely trending upwards over time. The increase since 1850 is maybe about a 40% rise. So again, going back to the question from earlier, is what we're doing actually making a significant difference? Yes, in terms of like a percentage, definitely. That the amount of carbon dioxide in the air has gone from maybe 290 parts per million up to over 400 parts per million today. Which, by the way, this graph is from 2014. The level is going up so fast that 2014 is already a long time ago. This is where we are today, actually off the scale of that graph already. We're up to about 410 parts per million right now. So in fact, the levels of greenhouse gases in the atmosphere have gone way up over the same time period that the temperature has gone way up. I also want to draw your attention to the fact that if you look at this graph of the greenhouse gas concentrations, that it has the same key feature. The carbon dioxide graph especially has the same key feature as the last graph, where our fossil fuel use took this dramatic upward turn in about 1950, and the amount of carbon dioxide in the atmosphere takes exactly the same upward turn in 1950. So that is a good piece of evidence that, in fact, the carbon dioxide in the air is coming from fossil fuel use, in case you want to make the objection that, well, just because carbon dioxide levels in the air are going up doesn't mean it's because of fossil fuel use. But I just showed you a minute ago that the fossil fuel use is turning upwards in exactly the same way that the carbon dioxide in the atmosphere is turning upwards. So that seems to strongly suggest that the two things are correlated with each other. So let me add that to my summary. So evidence number one, we know that we're releasing a lot of carbon dioxide into the air, largely since the 1950s because of fossil fuel use. And also carbon dioxide levels in the air have been building up largely since the 1950s. So over the same time period. Okay. Any questions so far, by the way? Feel free to chime in if you have questions. If not, I'll keep chipping away at the story. Okay. All right. Let me raise another objection. Just because carbon dioxide levels are going up, well, look, there's a 50-50 chance that carbon dioxide levels are going to be going up, just because if you flip a coin, there's a 50% chance they'll be going up or a 50% chance that they'll be going down. So just because the levels are going up doesn't necessarily mean anything. You know, what's the significance of that? How do we know that that's significant in any way? Don't the carbon dioxide levels naturally go up and down all the time? And yes, they do. Carbon dioxide levels do naturally go up and down over time. That is a correct statement. However, let's check whether the rise that we've seen in the late 20th, early 21st century is consistent with the rises that we've seen due to natural effects in the past. So here is the carbon dioxide level over time going back 800,000 years into geological history, where we actually, you know, look at the composition of rock and ice and all these things and try to figure out what the carbon dioxide level in the air was in ancient history and prehistoric times. And what we see is, yes, carbon dioxide levels do fluctuate naturally. They fluctuate approximately between 200 parts per million and 300 parts per million naturally. And we're currently above 400 parts per million. So we're way outside the range that we've ever seen from any kind of natural fluctuations. So that strongly suggests that something new is going on here that's never occurred before in human history. In the words of the IPCC report, atmospheric concentrations of carbon dioxide, methane, and nitrous oxide are at levels unprecedented in at least the last 800,000 years. So this is not something that's just like, well, it's gone up a little bit, but if we just wait 100 years or 1,000 years, it'll go back down. This is something that's way outside the range of natural fluctuations that we've ever observed in the past. Okay, so adding that to my summary, we know that we're releasing a lot of carbon dioxide into the air. We know that the carbon dioxide level in the air has gone up. We know that the carbon dioxide level in the air is higher than we've ever seen before. Another objection you might raise is, well, I gave you a putative reason why carbon dioxide level might cause an increase in temperature, but who's to say that's true? That was just a story. Maybe it doesn't matter if carbon dioxide levels go up. Maybe carbon dioxide is not really as important as everyone says. Maybe this has nothing to do with the global warming that we've seen, and it's really just a coincidence. Because again, like I was saying before, at any given moment, there's a 50-50 chance the carbon dioxide level is going up. At any given moment, there's a 50-50 chance the temperature is going up. So that means you have a 1 in 4 shot that at any moment in history, both of them will be going up at the same time. So, you know, maybe it's just chance that they both happen to be going up right now. Well, one way we can address that objection is to look, I just showed you the carbon dioxide levels throughout geological history. Let's look at the temperature levels as best as we can estimate them throughout geological history and see how they compare to the carbon dioxide levels in the past. And here's what we get for that. The blue, or just on an arbitrary scale, represents the carbon dioxide fluctuations over time. And this is mapped over the last 600,000 years on this graph. The red is how the temperature has changed over the last 600,000 years. And what you see is that if you just kind of look at those graphs next to each other, you can see that their shape is very similar. it definitely looks like they are correlated to each other. They both go up here, and then they go up here and stay up for a while. They both have this plateau here. They both have a spike here. They both have a spike here. It looks like all the spikes match up with each other. So that strongly suggests that they are related for some reason. This graph doesn't tell you why they might be related, but I've given you a plausible explanation of why it makes sense that they're related to each other. And then if you look at geological history, you see that in fact they are related to each other. So if we look back over the last 600,000 years, what we notice is that carbon dioxide and temperature pretty much always go up and down together and mirror each other. And so that makes sense, because if you assume that the greenhouse effect is correct, then the carbon dioxide level going up causes the temperature to go up. So that makes sense why they would go up and down together with each other, which is a concern because the carbon dioxide level has recently gone way up. So we would expect the temperature to follow it. And there's a question in the chat of how can you tell the levels of carbon dioxide so far into the past? I'm not like an expert on this or anything like that, but I know what they do is they look at, they have samples of these like deep ice from glaciers, and they have samples from rocks, and they have samples from, you know, these kind of like geological things that have been around for hundreds of thousands of years. And you look at the composition, like let's take ice, for example. Let's say that you dig up some ice that's way, way deep inside a glacier and has been frozen there for, you know, 100,000 years. And you study the exact composition of that ice. How much oxygen is in there? You know, how much carbon dioxide is frozen in there? What are all the different, I don't know the exact techniques they use, but they look at all the stuff that's in that ice, and they can deduce what must have been the composition of the air to produce, you know, that composition of ice. Like for instance, I don't know if this is exactly how they do it, but I'm speculating a little bit here. But for instance, one thing we're not going to talk about in this chapter is how water absorbs carbon dioxide. So the oceans and, you know, all the water on Earth has a tendency to become more acidic the more carbon dioxide is in the air. So I presume that like if you looked at ice, you could probably look at how much carbon dioxide was in there and infer that the amount of carbon dioxide in the ice is related to the amount of carbon dioxide that was in the air when that ice was formed, or, you know, probably something along those lines. So that's how they do it. So it's not as accurate. It's not as spot on accurate as the way that we can measure temperatures today. But you know, we do our best to estimate it as closely as we can. And this is the result that we get. Okay, another objection I wanted to mention, one that I heard a lot over the past few years. I think this became, you know, somebody's talking point for a while. You'll notice that in the greenhouse effect description, there's actually two reasons why the Earth's temperature might go up that are consistent with the basic physics I gave at the beginning of the class. The temperature could go up because less infrared light is escaping into outer space. That's the greenhouse effect. Or the temperature of the Earth could go up because more energy is reaching the Earth from the sun. So maybe the sun has gotten hotter and the sun is actually sending out more energy, and that's why the temperature of the Earth is going up. That, scientifically speaking, that makes sense. You know, that is a possible reason why the temperature of the Earth might go up. But we can check that. You'll notice the theme here is, you know, you want to raise an objection? Okay, we can check that. And we do. We measure the amount of energy that's coming out of the sun. Now, we don't know what the amount of energy coming out of the sun was hundreds of thousands of years ago or anything like that, but we can measure it over recent history. And it is true that the energy output of the sun actually does fluctuate over time. That's the red graph on the slide right now. And you can see it does go up and down a little bit on like a regular cycle, but it's not generally trending upwards over time. So that we don't have any evidence that the sun is giving off more energy now than it was, you know, 40 years ago. And yet the temperature of the Earth has clearly gone up over that period. So this does not seem to hold water at all, because we don't have any evidence that the temperature of the sun is going up or that the energy output of the sun is going up. And we do have evidence that the temperature of the earth has gone up over the same time period. So there's no evidence that this is actually, it makes scientific sense, but it's not consistent with any of the evidence that we have. So it doesn't seem to be correct. Okay, so once again, building up this summary, we know that we're releasing a lot of carbon dioxide into the air. We know that the carbon dioxide levels in the air have been building up. We know that they're at the highest level now that they've been in human history, in hundreds of thousands of years at least. We know that in the past, we've always seen that temperature and carbon dioxide go up and down together. We have a theoretical explanation for why carbon dioxide would cause the temperature to go up or down. And we ruled out the other obvious explanation for why the temperature might be going up. So all this evidence seems to be leading us to the same conclusion, that the explanation for why the temperature is going up is because the greenhouse gases in the atmosphere are going up, and the explanation for that is because of fossil fuel use. Okay, now, have I addressed every possible objection that you could make if you know the ins and outs of this? No, certainly not. There are many finer points that you can raise legitimate skepticism about. And it's actually interesting. The story of our textbook author, Richard Muller, is that he was a famous global warming skeptic. He's actually a very famous physicist who did a lot of really good work in a lot of different areas. And in like the kind of 90s era, he had a lot of legitimate skeptical questions about global warming that he felt were not answered by any of the data that was available at that time. And so he was kind of like a vocal expert who was saying, I don't necessarily agree with this scientific consensus. And but remember, this guy, he's not just some schmuck. He's a very famous physicist who thinks like a scientist. So his reaction to, I have a lot of skeptical questions which are not being answered, is, okay, I now have to answer all these questions and find out what the answer is. So his reaction was not just to deny that global warming existed. His reaction was to find out for himself what the answers to his questions were. So he started his own climate change study organization, which was basically a competitor for the IPCC and was designed to challenge the IPCC's conclusions and either debunk them or verify them, depending on what the reality was. As it turned out, his organization, he questioned whether the temperature data was correct, and he concluded that yes, the temperature actually has gone up, that's correct. He doubted that the temperature data, the reliable temperature data, only went back to 1850. So he was skeptical that, well, maybe that's just an anomaly. Maybe if we go back further than 1850, maybe it wouldn't go up. So he went back to 1750 using some new methods that he invented to make the temperature data much more accurate. And he found that if you go back to 1750, it doesn't make a difference in the conclusion. He created a bunch of computer models, computer simulations, which allowed him to consider different possible other explanations for global warming and see which ones actually were the most significant according to his computer simulations. And he found that the only two things which made any significant difference in the Earth's temperature in his simulations were carbon dioxide levels in the air and volcanic eruptions. Those were the only two that made any noticeable difference. And so his explanation is that in the graph you're seeing right now, the black line is the temperature measurements, and the red line is his computer simulations prediction of what the temperature should be. And he found that to get that level of accuracy, all he had to do was put in carbon dioxide in order to get that general upward trend, and to put in volcanic eruptions to give you those sudden dips that occur from time to time. Those correspond to major volcanic eruptions that have occurred in history. So he actually ended up finding that carbon dioxide that the temperature was going up, and that the main reason for it was the carbon dioxide concentration in the atmosphere. And here's a quote from him, kind of like summarizing the kind of end of that era of his project. He said, 3 years ago, I identified problems in the previous climate studies that, in my mind, threw doubt on the very existence of global warming. Last year, following an intensive research effort involving a dozen scientists, I concluded that global warming was real, that the prior estimates of the rate of warming were correct. I was not expecting this, but as a scientist, I feel it is my duty to let the evidence change my mind. If you ever want to read some of his other stuff, he has a really good book called Energy for Future Presidents, which is kind of like the sequel to our textbook, where he has some really good discussions about this. He talks about how he was always a skeptic, but he was never a denier, which he makes a distinction between those two things. That like a skeptic is someone who raises hard questions, but a denier is someone who doesn't want those questions to be answered. They're just raising questions just to create doubts, which is a different thing. And on the other end of the spectrum, he identifies, the difference between people who are legitimately making the case for global warming versus people who are, again, like determined that global warming is right no matter what the evidence is, which is also not good. So he had this is actually a great illustration of what the scientific method is all about and what scientific thinking is all about. That you raise skeptical questions, and you raise those questions as kind of a hypothesis, and then you test that hypothesis and figure out whether it's true or false. And people have kind of lost sight of the second half of that story of scientific thinking, that if you want to raise skeptical questions, that's great, but then you have to answer those questions and live with whatever the answer is based on what the evidence is. Which I'll talk a little bit more about that momentarily. But first, let me not get sidetracked yet. I want to kind of summarize the main conclusions again. We know that we're releasing a lot of carbon dioxide into the air. We know that it's mostly because of fossil fuel use. We believe that if carbon dioxide gets emitted into the air, there's no good mechanism for how it gets removed naturally. We've seen that the carbon dioxide levels have been increasing along with fossil fuel use. We know that the carbon dioxide levels are the highest they've ever been in human history. And we know that in history, whenever the carbon dioxide levels go up, it almost always it's almost always correlated with the temperature going up, at least. We have a theoretical explanation for why this makes sense because of the greenhouse effect. And the calculations and computer simulations agree that carbon dioxide is the main driver for increasing the temperature of the Earth. So again, like I said off the top of this section, one thing I want to emphasize is that any one of those pieces of evidence by itself is not a convincing explanation for why global warming is caused by human beings. But what makes this conclusion so strong is that it's a lot of pieces of evidence that are all pointing you towards the same conclusion. So even if not every single one of those turns out to be, on the right track, because from time to time, in the world of science, things do get turned upside down and disproved and et cetera, et cetera. So it's hard to be confident in something if it's just supported by one experiment or one measurement. But if you have a lot of experiments and a lot of measurements all giving you the same conclusion, it's a much more robust conclusion that's hard to debunk. Maybe we don't fully understand the situation, but at least it generally doesn't get, fully debunked. And that conclusion right now is that carbon dioxide that's put into the air by human beings is what's causing the temperature of the Earth to go up. Okay. And because that conclusion is so important, let me give you a few other statements of it. This is what the IPCC, this was kind of like extracting from the IPCC report. I think this is the clearest statement they have of what their conclusion really is. They say atmospheric concentrations of carbon dioxide, methane, and nitrous oxide are at levels unprecedented in at least the last 800,000 years. Their effects, together with those of other anthropogenic drivers, which remember means man-made effects, are extremely likely, and in their language, extremely likely means that they are at least 95% confident about what they're about to say. So that that man-made effects are extremely likely to have been the dominant cause of the observed warming since the mid-20th century. So that's what the IPCC, that's as far as the IPCC is willing to go, at least in 2014, that man-made effects are at least 95% likely to be the main cause of global warming since at least the mid-20th century. Okay. Here's the Berkeley Earth Project's conclusion. This is actually coming from Muller's book, but this is basically the clearest statement I could find about it. He says the exquisite agreement between the warming and the carbon dioxide suggests that most, maybe all, of the warming of the past 250 years was caused by humans. So it's the same basic conclusion. There's some disagreement about, did global warming start, more like in the mid-20th century, or can we confidently go further back than that and stuff like that? But the essential conclusion is the same, that it's human beings creating fossil fuels, creating carbon dioxide through the use of fossil fuels, driving the temperature upward. Okay. Going back to my little tangent that I was about to go on a few minutes ago, I did actually want to build a few minutes into my presentation to go off on that tangent because I think it's an important tangent to go on with a lot of things that are happening over the past few years. Global warming being maybe the most famous example, but there's a lot of other examples as well. That this kind of, what is scientific thinking and like what's the purpose of it? And believe it or not, the best quote I could actually find for this, it comes from, I don't know if you guys played the computer game, the Talos Principle, which contains a lot of like kind of philosophical rambling. And here's one of the quotes from that game. They say to doubt everything, but I disagree. Doubt is useful in small amounts, but too much of it leads to apathy and confusion. Don't doubt everything, question everything. That's the real trick. Doubt is just a lack of certainty. If you doubt everything, you'll doubt evolution, science, faith, morality, and even reality itself, and you'll end up with nothing because doubt doesn't give anything back. But questions have answers. If you question everything, you'll find that a lot of what you believe is untrue, but you might also discover that some things are true. You might discover that what your own beliefs are, and then you'll question them again and again, eliminating flaws, discovering lies until you get as close to the truth as you can. Questioning is a lifelong process, and that's precisely what makes it so unlike doubt. Questioning engages with reality, interrogating all it sees. Questioning leads to a constant assault on the intellectual status quo, whereas doubt is far more likely to lead to resigned acceptance. After all, when the possibility of truth is doubtful, why not simply play along with the most convenient lie? So that's really something I think to keep in mind, that yes, skepticism and things like that are extremely important. And we all know that there's so much stuff that you can't believe floating out there that you have to be able to ask skeptical questions about, is this actually true? What I just saw, is what this person said actually true? But at the same time, you can't just say, well, I don't believe you, so therefore I'm just going to get rid of any evidence that doesn't go with what I already believe, which is what a lot of people do. I remember one time it was actually a funny story. It was literally one semester, the day that I had spent my entire 8-hour day at work reading about all this global warming stuff because I was updating this PowerPoint presentation for one semester. And on my way home, I was talking to someone on the phone who, doesn't really believe in global warming. And somehow it came up. I guess I probably told them what I was doing that day. And they asked, as a rhetorical question, they asked me, well, how do we know that this is true anyway? And I was like, well, and I had the answer on the tip of my brain because I had just prepared this presentation. So I talked for like 5 minutes about all, just like I did for you, about listing all the evidence. And then their response was, well, I don't believe that. I was like, well, I don't know how to talk to you then. If you're just going to say, I don't believe whatever I don't like, then, that's a total disconnect from reality. But by the same token, you can't just say, well, I trust this person, so I'm going to believe them either. And that's where kind of scientific thinking comes in, and critical thinking comes in, and what you're supposed to learn from a course like this and gen ed courses, and what their purpose is when you go to like this university, is to kind of learn how to ask critical questions, which then have to be answered. And then the second half of that story is the onus is now on you after you've asked that skeptical question to get it answered, like our textbook author did. Sometimes the person you're talking to doesn't have the answer. Doesn't necessarily mean that they're wrong. It means that now you have just made some work for yourself, because you now have to find the correct answer to that question, which is actually based on reality and evidence. And then let that either reaffirm your belief or change your mind. That's the other piece of this, by the way. And another big part of scientific thinking that people don't talk about is that science also requires you to, kind of not have too much of an ego about your beliefs. And sometimes when you ask a question in the world of science and you do the experiment shows you are wrong. You are totally wrong about this. That's fine in the world of science. That's fine to be proven wrong, because that's still progress. All you do, if you're proven wrong, all you do is eat crow, change your opinion, and say, okay, I stand corrected. And now everyone is in agreement, because, you got correct. You turned out to be the one that was wrong, but you got corrected. That's also fine. But you have to base, where you fall there on reality, and not based on what you want to be true. And that's kind of the bigger story of this section. Okay, questions? Any questions about this section? Things I didn't address? If not for the last few minutes, I'd like to very, very quickly breeze through the next section, which is, I just don't have time, because we only have one more class left, and I know what I want to talk about next class. This section is going to get glossed over. I think it's mostly stuff that you kind of already know from just what you've heard. But let me just flip through it really quickly, which is the question of what's the bad thing? What's the problem with global warming? Why is it bad? What are the negative consequences of it going to be? What is so bad about an extra couple degrees Celsius? So that's the first thing to draw your attention to, is a lot of people misunderstand the amount of warming that we've actually had. It's actually not that much, in a sense. It's only maybe 1 degree Celsius, 1.5 degrees Celsius of warming, which really doesn't sound like that much. It's just a couple degrees, 2-3 degrees Fahrenheit maybe. So you might wonder, how can that be such a big deal? And the short answer is, it's not that much of a big deal. What's a big deal is that it's still going up, and we're expecting it to go up a lot more than that. So the amount of warming that's occurred so far has not caused any really significant effects, which is why a lot of people don't take it too seriously, but it's likely going to by the end of the 21st century. That's the problem, because there are no signs that this problem is going to go away anytime soon. So what are we expecting to happen then? We are expecting the continued emission of greenhouse gases will cause further warming of the Earth, and it will cause long-lasting changes in all components of the climate system, increasing the likelihood of severe, pervasive, and irreversible impacts. Okay. We're expecting temperatures to rise over the 21st century, no matter what we do. And it's very likely that heat waves will occur more often and last longer, that extreme precipitation events will become more intense and frequent, that the ocean will continue to warm and acidify, that the sea level will continue to rise. We are expecting that there will be substantial species extinction, global and regional food insecurity, constraints on human activity. In other words, human civilization is going to have to be changed because we won't be able to continue, with what we're doing. And there will be limited potential for adaptation, which in the jargon of the global warming world, adaptation basically means using technology to, offset the increase in temperature. And so there will be a limited potential that human technology will actually be able to protect us from the warming eventually. Someone asked in the chat, which types of animals would go first? Short answer to that question is ones that are unable to migrate to new habitats that suit their needs. What happens most of the time is as the warming occurs, animals will try to migrate with the warming so that they can stay in a habitat that's similar to what they're used to in a different area. So animals that migrate to new areas very slowly are very vulnerable. And of course, animals that are in habitats which will no longer exist, like, the kind of the story of polar bears and that kind of things, they have nowhere to go because they're at the edge already. They can't migrate to a new habitat. Along the lines of that question, the next slide is actually partially answers that question as well. A large fraction of species face increased extinction risk due to climate change. Actually, most plant species will not be able to migrate to new habitats fast enough because, of course, plants migrate to new habitats very slowly, only doing so from generation to generation. So plants are in a special danger, and also animals that can't migrate to the new habitats that they need quickly enough. We're also expecting this to cause problems for food production and food security for a variety of reasons. If we can hold the warming under 2 degrees Celsius, which is kind of the goal for the 21st century, we do expect it to negatively impact food production, but in a way that's maybe manageable. If it gets much higher than 2 degrees Celsius, we're expecting it to pose large risks to food security globally. So that's where it starts to become more catastrophic, which we'll get into that issue next class of the different possible scenarios. Some likely things that will happen in populated areas, like say Philadelphia, would be heat stress, storms, extreme precipitation, inland and coastal flooding, landslides, air pollution, drought, water scarcity, sea level rise, and storm surges. If you're in a more rural area, your main problems will be water availability and supply, food security, infrastructure and agricultural incomes, including shifts in the production areas of food and non-food crops. Okay, and those things that I just listed off are sort of considered to be the likely problems that we're going to face in sort of the late 21st century. There's also a whole second category of more serious problems that are less likely, but it's a little bit worrisome that they're possible at all. There are what they call tipping points in the climate. And those tipping points are basically certain temperature thresholds, which once they are crossed, it triggers some kind of like major event that cannot really be undone. A big example of this would be one thing we're a little bit worried about is that if the temperature gets sufficiently high, the entire Antarctic ice sheet could start to slide off of, Antarctica is actually land covered by ice, unlike the North Pole. So what could actually happen is that the ice slides off the land and goes into the ocean. And then what happens is it's like dropping an ice cube into your drink. The water level then suddenly goes way up. And that could cause several meters of sea level rise in a very short period of time. So that would be like a major catastrophe, but we have no idea when or if that would occur. We don't know what temperature it would take for something like that to be triggered. So that's a big problem. Another similar one that I've heard people talk about is when it comes to the Arctic Ocean. The Arctic Ocean contains a huge amount of methane, which is a greenhouse gas. And as the Arctic Ocean warms up, it can't hold as much methane anymore. The warmer it is, the less methane it can actually hold. So as the ocean warms, the ocean then starts giving off greenhouse gases, which again, if that started happening, even if we completely stopped using fossil fuels, there would then be a natural source of global warming that would be really, we wouldn't be able to do anything about. And then like a natural process could take over and start producing even more global warming than what people are producing. And, you know, we can call it natural, which sounds good, but that, you know, just because it's a natural process doesn't mean that it doesn't totally mess up human society. And who knows how much higher the temperature could get up if we get into one of those crazy cycles. And here's a couple quotes about that from Richard Muller. The scary thing about tipping points is not that they are considered a current danger, because they are not. These are all, what I'm describing there are probably not going to happen. The problem is that smart people keep thinking up ones that we hadn't previously recognized. The really dangerous tipping point is the one that is real and has not yet been recognized. Or in the words of Elon Musk, we're currently running the most dangerous experiment in history, which is to see how much carbon dioxide the atmosphere can handle before there's an environmental catastrophe. And we don't know the answer to that question exactly. So there's, in some sense, there's no safe level of warming. We can't guarantee anyway what's going to happen with any particular level of warming. We have estimates of how much warming we can probably handle. And those estimates are, we can probably handle 1.5 to 2 degrees Celsius of warming comfortably. But we'll talk next class about how realistic it is that we can actually keep the warming below the levels that we actually think are highly dangerous. And that'll be kind of what the whole next class is all about. Okay. So other questions, any questions people wanted to ask? Questions? I'll quit the lecture material there. This is a good stopping point. Next class will be much more focused on like, what do we actually need to do to prevent this from becoming a major problem? Like, which countries need to do something? What do they need to do? When do they need to do it? What can you personally do? What should you be doing to you know, make your contribution to helping and all that type of stuff. So next class will be kind of like, today's class was kind of like convincing the skeptics or arming the non-skeptics with the foundational knowledge you need to sort of accept what global warming is and what's causing it. Next class is much more kind of solution oriented of who's responsible for global warming, who should be responsible for fixing it, and how should they fix it. Okay. So any other questions that people wanted to ask before the end? Okay, well, I guess I'll quit there then and start switching over to my other class. So thanks for coming. Definitely make sure you come Thursday. I'm working on arranging for a guest speaker to come and talk about some things as well. And I'll give my 2 cents on what's going on. So we'll pick up there for our last class of the semester. All right, so I'll see you later then. Bye. Hope you learned something.
Thank you.
My daughter says bye in the background.